All right. Then I got how am I? Welcome to Toy World Geospatial Research Institute's seminar series for June. And hey, we've grown a bit for a seminar. Catherine here is clearly a really nice draw card, and we really appreciate you coming in today to speak to us. I'll go through a little bit about your profile. It's quite long.
You don't have to read it all.
So Katherine is an Australian astronaut and accomplished space systems engineer, recognised as the first professional astronaut to officially represent Australia and named the 2026 Australian of the Year. So welcome to New Zealand.
Thank you.
She graduated in April 2024 from the European Space Agency's 13-month astronaut basic training as part of the Hoppers class after being selected from over 22,500 applicants in 2022. She currently serves as the director of the Australian Space Agency, where she has played a key role in advancing the nation's space capability. Her work includes leading technical planning for the Moon to Mars rover lunar mission, strengthening Australia's space strategy and overseeing initiatives in satellites, infrastructure, and launch systems. She has a 15-year international career across 6 countries, and she's contributed to a wide range of space programs, including the Orion spacecraft for NASA's Artemis missions, space station systems, Earth observation, and robotic technologies such as satellite capture and debris removal. She holds 4 degrees in science and engineering and an honorary doctorate. Group captain in the Air Force Reserve, she has also earned top honors in military training. Beyond her professional work, she volunteers, mentors young engineers, and actively participates in community and international leadership initiatives, which I think this counts as one of those. And let's welcome Catherine to.
Thank you so much for having me. Tēnā koutou, tēnā koutou, tēnā koutou katoa. It's great to be here at the University of Canterbury and have the chance to speak with so many of you and to meet so many of you, I hope, as well, to talk about space and astronaut training. And I'm going to take you through a presentation that talks a bit about space, a bit about my training, a bit about the future of what's coming up in space. And I'm also very happy at the end to take any question that you may have for me, and I'll do my best to answer it as well. For tens of thousands of years and more, humans have been looking to the sky to guide our lives, right? It's absolutely incredible, the heritage that we have here, especially in our region. Today that continues, but we can also look down from the sky to guide our lives. Here is an image taken from the International Space Station of New Zealand, and it looks absolutely beautiful from up there, I'm told. I've not been to space yet, but I'm told by the astronauts that do that they're absolutely blown away when they look back at the Earth, particularly when they look into that horizon that bends around the Earth, that thin blue line of air within which all life as we know it has evolved and existed, except for astronauts and any passengers on the spaceships they take up with them. And 90% of the atmosphere is actually below where an aircraft flies at about 10 kilometers. So it's incredibly thin. And up there, you can't see borders unless it's nighttime, and you can see the difference in development. But you can see pollution, you can see humanity's impact on the planet. And when astronauts return to Earth, they're often returned compelled to protect it and understand it and know that we all have our part to play in that. We're really blessed, I think, in this part of the world to live under such a beautiful night sky. Here in a city, you could see probably about 400 or 500 stars with your eyes. If you get out into the countryside on a clear night, you might see 4,000, which is amazing. But even bigger than that, our Milky Way galaxy, we think, has up to 400 billion stars. And we know from looking at those closest to us that almost all of them probably have exoplanets. So just in our Milky Way galaxy alone, we calculate that there's about 9 billion Earth-like exoplanets sitting within the habitable zone, which is amazing. Here's an artist's impression of a number of the icy and rocky worlds. We can't see them like this, but we know a lot about their composition through what we can detect. And I think that's just mind-blowing, considering that in our universe, there are probably up to 2 trillion galaxies. So when you add that up from a star number perspective, it's very similar to Avogadro's number, which is also very similar by chance to all the grains of sand on all the beaches and the oceans and the deserts in the world. So the scale of the universe is mind-blowing, and we're only just at the beginning of understanding it and learning from it as well. Because when we go up into space, we don't go up there for space's sake. We go up there for humanity's sake and for Earth's sake. There's quite a misconception that when people are involved in space, they put a suitcase of cash in the top of a rocket and launch it out of our atmosphere. But in fact, the dollar spent on space is a dollar spent on Earth. And that dollar usually gives returns and dividends. At the Australian Space Agency, our exploration program alone is returning at least $7 for every $1 of taxpayers' funding invested in it. And the global space economy is set to triple over the next decade. And that prediction was done before the SpaceX IPO. So who knows what the future may hold for us now. We need some economists to redo those predictions. But all that to say is we can access that growth and that opportunity here in New Zealand. You already are with companies like Rocket Lab and others, but there's more opportunity to be gained if we're able to deliver greater operational capability into the international marketplace. We have to move beyond demonstration to operation. But ultimately, we have all that space utility because space is just an eye in the sky, right? It's a place up there. It's a place that, just like the ocean, has breadth. And we're only just beginning to imagine what we can do with it. So from this eye in the sky, we can see phenomenon all around the world. You can see anything from the International Space Station, which is 200 kilometers up. This video wasn't taken from the space station, but it was a similar altitude. And you can see anything that is bigger than about 120 meters with your eye. So you could see this university. You can see the Bledisloe Cup stadiums, but thankfully not the scoreboard. I think the typical maximum resolution for a lot of commercials is about the size of a sheep, I'm told, which is an interesting unit. And the day side of the planet, you can't see text, that's just helpful, but you can see a lot. You can see the perspective from clouds. You can see a lot more in other parts of the spectrum as well. There's still a lot we don't detect. I heard recently that we don't detect, for example, from any satellite, the particular spectra of eucalyptus forests, which would be the best to indicate bushfire loads, for example. So by contributing capabilities that meet our national needs, in that case, particularly for Australia, we can help address unique needs for our nation. From this high point in the sky, what you can see, you can connect. Just like a super high mobile phone tower, you can connect anything you see, and then you can connect to other satellites and what they can see as well. And it's for that reason that we are about to have global connectivity direct devices from satellites in the next few years across Australia and soon across other parts of the world too, which will be absolutely game-changing for safety as well as in the future for industries. It helps us to collect and communicate climate data. Today, 99% of climate data by volume comes from satellites in space, and together connectivity and what you can see, the remote sensing, and what you can send along those connections, it means that space is critical to addressing every single one of the United Nations Sustainable Development Goals. At the UN, there's an Office of Outer Space Affairs that works on how to do that, UNOSA. Space is also a place for discovery and for exploration. And that, again, is for the benefit of us on Earth. I think discovery, that desire to explore and understand our world, is part of what it means to be human. I heard a quote recently from Søren Kierkegaard, which was, to dare is to lose oneself momentarily, but not to dare is to lose oneself. In space, losing your footing is a literal daily reality, but when looking to move forward, it's that leap in the dark that is necessary to discover that moment of instability. And that's something that humans have understood for a long time. It's that feeling, I think, that most young kids have when you want to look under a rock to see if there's a bug, or climb a tree to see if you can, or to climb a mountain to look at the view. And it's that feeling you get, you know, when you lie on your back and you look up and gaze at the stars. And it's that drive that has led humans to, you know, go further around our world than ever before, and perhaps to go further in space as well. This is a photo of me in year 8. I was obviously a pretty cool kid in year 8. As my first trip to NASA, and at that age, I was amazed by space. I used to love lying on my grass in my backyard where I grew up in the north of Sydney and looking up at the stars. And my parents were accountants, but my mum had studied physics, so was able to explain some of what I was looking at. And I remember her telling me that some of those stars aren't stars, they're planets, and no one's ever seen a planet up close with their own eyes before. And as a kid in early primary school, that just sounded like the greatest adventure of all. And as I grew up a bit about this age, I started to fall in love with science and reading science magazines and science books. And I really wanted to explore then for the discoveries I could perhaps be part of helping unlock. And I liked bushwalking and sports far more than school. But it meant that school became relevant to learn to have the tools to perhaps one day be an astronaut. And in year 8, same age this was taken, our school asked us to write down 3 things we wanted to be when we grew up. And I just wrote astronaut and refused to fill out the other 2 because I couldn't think of anything greater that I wanted to do with my life. And instead of making fun of me, my school, my parents, they said, well, go figure out what that would actually take. Probably hoping I'd see sense, probably hoping I'd see how unlikely it is. And I did see how unlikely it is. I learned that Australia didn't have a space agency. Our space agency was only set up in 2018. I learned there's no path to being an astronaut. If there was a checklist to follow, it would have said 1, leave Australia, and 2, good luck, right? But I learned that to be an astronaut, it is possible. 2 Australians had been to space before, but representing NASA, they got dual citizenship. So I thought my life would have to be overseas. I realized that to be an astronaut, you can't just finish school and become an astronaut. You need a first career. And your first career can be a scientist of any kind, an engineer of any kind, a medical doctor or a pilot, ideally a test pilot, and you need at least a master's degree plus 3 years experience in those fields, ideally a second master's degree in another STEM field or a PhD. I learned that you need to have what's called expeditionary behaviors and experience. That means the kind of person you want to go camping with or live in a caravan with for a long time. So you need to have experience, for example, in the military or exploring Antarctica or with Doctors or Engineers Without Borders, living away from home, doing important work for at least 6 weeks continuous. I learned that you need operational skills. That means being able to make decisions that could be fatal to yourself or others in a timely manner. That can mean being in the emergency services or the military again, or being a pilot, scuba diver, skydiver, all of those are relevant. I learned you need to be fit and healthy, not an Olympic athlete, but fit and healthy, so you can have a long career and be safe in space. And you should be internationally minded, ideally speak another language, and basically build out your career knowing that astronaut criteria do shift a little bit over time as well. But what I thought was great is that all of those options sounded like a great adventure. And the hard thing was to pick what I wanted to do. And I loved aerobatic flying later in high school. And it made everything very real to me. Ultimately, I chose to study science and engineering, a double degree at uni in physics, maths, and aeronautical space engineering. But when I finished my undergraduate degrees, I went overseas because I couldn't see a way at that time to having a space career in Australia. I wanted to build big, beautiful science and exploration missions, and I didn't see a way to do that then. Thankfully, both in Australia and New Zealand, that has changed now, and there are really good careers in both of our countries, but it's taken time to build out those ecosystems, and there's still more to do. So I went overseas. I worked as a space engineer on some of the coolest missions I could have ever hoped to work on. And then learning from some of the best in the world. When the Australian Space Agency set up, I went back to Australia and was able to help grow the Australian space sector, which is really awesome. I finally got my chance to apply to become an astronaut in 2021. In 2021, the European Space Agency put out their first call for astronauts in more than about 12 years. And I was able to apply because I have 2 passports. I'm also British, inherited through my mother. And there's never been a call to date for Australian astronauts by the Australian government or Kiwi astronauts from the New Zealand government. Perhaps I can show the value and help accelerate the time to that. But the astronaut selection was absolutely incredible. It was just like the movies. I remember seeing the ad on my WhatsApp lit up because me and all my friends who had been waiting our whole careers to have the chance to apply finally knew we had our chance. And you rush to check the criteria and check you meet them all. And luckily I did. And I applied along with almost 23,000 others that also met every single point of the criteria from across the 22 nations that make up the European Space Agency. The criteria to be a government astronaut out of the International Space Station partners is the same. So it's the same at NASA, at Canada, in Japan, across Europe, including the UK, in Russia as well, and now also the UAE and India is an emerging partner. And but countries sometimes add on extra criteria, like you must have spent X time in the military, for example. There were 6 knockout rounds, 5 in person in Europe. Had to get over there and back in COVID, quarantining a lot on return. The first round was psychometric testing, sitting behind a screen, basically for 12 hours in a group of about 40 of you. There were about 13 or 1400 people left at that point, and they tested everything you can imagine on a computer: concentration, maths, physics, basic electronics, reaction times, the ability to multitask, memory in different ways. And you got 3 weeks morning you were going, and you got practice tests for those 3 weeks. And they invited people over a span of about 6 months in batches. So I was waking up every morning at like 3 a.m. to check my phone to see if I got an invite. So there wasn't a lot of sleep. I remember them taking it so seriously that we took 10 minutes to usher like a fly out of the room during the concentration part of the test. The next round after that was psychology. We went in groups of 7s or 8s to the European Astronaut Centre for a couple of days, and we were followed around by a couple of astronauts that were saying if, you know, are we the kind of person they'd want to go to space with and put their lives in our hands. A lot of psychologists, and we did stress tests in teams. They were looking to make sure we're adaptable under pressure and we're not under pressure, and that we don't have aggressive tendencies or too much of a self-depreciating tendency, and we had a healthy relationship with risk. And there were some really hard interviews in that as well. I can't go into too much details. There is an NDA, but it was pretty interesting. After that was the medical round. And in the medical round, we lived in a hospital for about a week, half of us in Germany, half of us in France. I was in France. And at that point, there were about 90 people left, and they did every test you could imagine without a scalpel. We were told there would be fitness tests, but not what they would be. We were told that, you know, you won't have a right of reply. So if you have an issue, put it on the table. So that was incredible. And I expected I wouldn't get through that. I've had 2 kids. One was a C-section. I was in my mid-30s. You know, you have life behind you. And I figured a few things would exclude me. But in the end, I got through. And that amazed me. And it was kind of like game on. And the last 2 rounds were panel interviews. They were making sure we understood the downside of being an astronaut. We had impromptu speeches. They'd throw us questions in foreign languages on our CV. It was quite amazing. And at the end, I was amongst the group of 23 that passed, which blew my mind. And you get to that point and you're like, why me? And not all those other amazing people. And you realize it's not a healthy use of your energy. And you need to focus forward and just keep preparing to become good enough in your own mind, and hopefully the selector's mind too. But then something amazing happened. The European Space Agency reached out to the Australian government and said that they would take me on the training if I represented Australia. I haven't really lived in the UK very long as an adult. I'd never lived there as a kid. I wasn't born there. So it would have been difficult for young people there to see themselves in me, especially when there's other good British candidates. So Australia got given an incredible opportunity, and I'm so grateful the government said yes for me training, representing Australia, and to bring the knowledge and insights home to inform the Australian space sector, and to have this option going forward. So I got to start at the Astronaut Centre in my class called the Hoppers. That's the patch I wear on my right shoulder. The 6 of us were trained, and we're all got different backgrounds. So at the top left is Pablo. Pablo is from Spain. He's an aeronautical engineer. Sophie in the middle is in space right now, 100 days into a mission. She's a helicopter test pilot and an engineer. On the top right is Marco. Marco's from Switzerland. He's a paratrooper, an emergency alpine rescue doctor, and a urologist. On the bottom right is Raphael. Raphael is an engineer and a neuroscientist and a hot air balloon pilot. In the middle at the bottom is Rose. Rose is an astrophysicist from the UK and a naval reservist as well. And we weren't called astronauts right away. You might notice that the patch here is different. This was taken at the beginning of our training before we had our wings. You call an ASCAN, which is kind of a mean word for astronaut candidate. And that's what you're called until you hopefully get through the gauntlet that's called astronaut basic training or ASCAN training. And it's the training that brings all these people from different backgrounds up to the same generalist astronaut qualification. So you can be picked for any role on a mission, except usually commander. Usually you need a mission under your belt before you can start in your second or later mission. So basically we did this training based in Germany at the European Astronaut Center with the European Space Agency. It's the same kind of core curriculum that all the International Space Station partners have around the world, but they all do it slightly differently. For us, they compressed it into 13 months because the mission Sophie's on needed to be filled and we needed to have all of us ready just in case. In this training, we study a huge breadth of topics because in space today, you go up there for many months, typically a 6-month mission on the International Space Station. So you need to be able to do lots of work. Here's us arriving on day 1 at the training. We do a lot of health and fitness because you need to be fit to go to space and to have a long career in space and to know how to use all the equipment up there. We go in centrifuges as well to get used to the space environment and to know that we can be performant up there. We learn how to do spacewalks in deep pools underwater around full-scale mock-ups of the International Space Station. We do a lot of scientific work, particularly in labs, because you're a scientist in the sky, or more accurately, a lab technician in the sky for every field of science. We do survival trainings, winter survival, ocean survival, firefighting and rescue. We learn how to drive the large rope International Space Station that's 17 meters long plus attachments, although that bit of training comes later. We do human behavior and performance training. That is how to build and develop out teams where you build trust quickly and can be highly performant in complex environments. We learn space trade skills or trade skills to be applied to space because up there's no can't call a plumber to come help out. You've got to do everything as a crew on your own. You also learn about all the facilities that you'll be using up there. You study humanities as well. We studied space history, space law, space economics. We learned about the strategy of different space agencies around the world. We had to learn Russian, which was the hardest thing for me. We had 8 weeks of lessons, so 50% of our time over 4 months to get to solid professional proficiency or advanced Russian. So yeah, that was definitely the hard part for me, but luckily I got through it. And then the list goes on and on. It was absolutely incredible. And it was a real privilege to do this representing Australia. I remember when I walked into a month into our training, we finally got our blue flight suits the same day that photo on the previous slide was taken. And I remember walking into the room and you see all the blue flight suits hanging up at the back and I spotted the Australian flag on mine. And it was quite a moment because it said so loudly to me about how much bigger this is than myself. It's the first time an Australian flag's ever been on an astronaut uniform. And it said to me that a door had been opened for Australia to take its place at the cutting edge of the cutting edge, to showcase what we're made of for our researchers and our industry to access the unique environment that is space. And for, I hope, one day there to be more Australian astronauts. So this is the International Space Station. It's the main home of astronauts in space today. It is huge. It's the size of a soccer field. It was built mostly about 25 years ago with some add-ons since then. And for almost 26 years, there's always been a crew on it. So it's never been never been uninhabited for most of your lifetimes. There's always been astronauts up there doing incredible work, including work I understand developed here at the University of Canterbury, which is awesome. So the parts that are cylinders in there, they're about the size of caravans to buses, and they have air inside. So you have a shirt sleeve environment. On the outside, you can put different experiments like cameras looking at the Earth or the sun or the stars, or have fundamental physics experiments too, or space environment sensing experiments. It is, a huge space station, and then we won't see anything else like it for a very long time. It's made up of huge international partnerships, and it's really been effective at fostering positive diplomacy between nations that get along and some that don't always get along. So it's been nominated for the Nobel Peace Prize twice, actually. I think 2013 and 2014. Hasn't got it yet. But when you can look at species level discovery, people can agree on that, even if they can't agree on much else. And that keeps ways of working and dialogue open between countries. I think there's been, as of last year, 4,400 peer-reviewed research papers published from the research up there, and noting that it takes a long time to get a lot of that work published is quite remarkable. Up there, astronauts are also guinea pigs because of the weird and wonderful things that happen to our bodies in space. Every single system of the body changes in certain ways up there. One of the ones most people know about is bones. Our bodies are the ultimate adapters. Our bones don't need to be as strong. Our muscles don't need to be as strong to live in 0G. So your body gets rid of what it doesn't need. Right away, you're effectively peeing out your bones, right? And if you don't do countermeasures, you're going to lose about 2% bone mass a month. The countermeasures are 2 hours a day in the gym up there and eating right. You can't take calcium pills because your body isn't hungry for calcium, so you'll get kidney stones. So you have to give it, make your body demand it. And so we test subjects for osteoporosis and osteopenia more broadly. And that's one of the reasons that we need more women in space too, because if women aren't in space, we don't have women on Earth benefiting from the medical research that's being done up there beyond the performance in teams being better, usually when they're more diverse. Inside the space station, we don't spin anything up. There's no artificial gravity. You float everywhere. So your hair goes a bit crazy. I'm told it doesn't fall out, but it does filter a lot of dust out. So your hairbrush is pretty manky. Things float. So you use a lot of Velcro and straps to hold things down. And we're told if you can't find something, it's probably floating above your heads. For similar reasons, you can't eat anything that creates crumbs because it'll get in someone else's ear or nose or some equipment. And so you can't have bread, for example, but you can have pancakes, tortillas, and pizza. You can't have anything that's really fresh food up there that's brought from Earth because it could become a food poisoning risk. So it's kind of like eating camping food, and astronauts just really crave like fresh fruit and veg. So maybe sometimes on a special occasion like Christmas, someone will bring up with an approved, probably very irradiated bag of oranges, and it's like a big celebration that everyone gets to enjoy that. And there's a big psychological element to eating and sharing food. So when you go up, you get to take about 30% of your food as preference food, potentially from your country qualified for space. So I will make it my mission to qualify pavlova under the Australian flag and settle that debate once and for all. I'll show you some parts of my training now that I really enjoyed. This is the centrifuge. So the centrifuge is where you spun up to feel hypergravity, high gravity. They're instrumenting me up here to make sure I can handle it. That my hand is on like an emergency stop lever, which I don't know what that would do to me. It would be quite a jolt. And they also handed me a sick bag, which luckily I didn't need at 6G, which is what they take us to. It's different to being a fighter pilot. If you're a fighter pilot and you pull back on the stick, the blood is pulled to your feet. And so when you see videos of people in centrifuges with their faces warping and passing out, it's usually due to that. Astronauts lie on their back on the top of a rocket, like a chair leant back on the floor, same at the top of a capsule. And that's done because our bodies tolerate G-force better this way because it doesn't starve our brain of oxygen. It is hard to breathe though, and your brain can be pushed to the back of your skull, which can cause cognition issues too. But because we have to hold high G for many minutes, it's a better way to do it. And so that was really about giving us the techniques to breathe through it. You kind of have to take small sips of air, not fully inflate your lungs, and kind of breathe perpendicular to the G-force direction. And it was really fun. Like we went through the profile of the Soyuz and SpaceX Dragon launches and reentries, and you could really imagine from a G-force perspective, at least, that you're on the top of a rocket or in a capsule returning to Earth. And it was quite interesting because the inner ear plays weird tricks on you. As the stages drop off these rockets, they're cold stage, not hot staged in a way that you feel it. So you're effectively in weightlessness between the stages and it feels like you're tumbling. You're not tumbling, it's just your inner ear doing weird things. And it was good to experience that before thinking it was the tumbling. This is us on a 0G flight or parabolic flight or vomit comet. Luckily, no vomit here from any astronauts, just some of our trainers. And you can see lots of flags on our shoulders. There's about 90 active astronauts in the world today, and we all often train together, particularly on training like this. You can see some of our Japanese counterparts there from JAXA having a ball. And this flight was the first time we were together in 0G. Some of us, like myself, had been on flights like this before in our previous careers, but it was a special experience. And as you fly through, you're in one of those planes. I think it helps to remind us what 0G really means. In a normal plane, you feel 1G, right? If it's flying straight and level. If you're falling at the same rate of the things that are falling around you, like that plane, I'm basically skydiving inside a plummeting plane, it's weightlessness, it's 0G. Also internally to your body, because your body is all falling at the same rate. Nothing is holding it up. If the space station at 400 kilometers up was on a pole, you would feel 90% G. You wouldn't be in weightlessness. Weightlessness is falling together. So when you're inside a space station in orbit, you are falling around the Earth. And that's what 0G is. Here's another flight that we're on, and this has got a few stations where we're learning how to get around, in this case using our feet. You can see we're not particularly great at it. It's really hard to have the right lateral stability, and you don't have the same proprioception, the same understanding of where your body is. And it's immediately disorienting. You have to use visual clues. And the guy there that lost his footing, Slavoj, he's already been to space and back since this video, and he did just fine. So there's hope for me yet. In terms of my ability to get around using my feet, and in space, the top of your feet actually get quite rough as opposed to the bottom. Here, the instructor is showing me like that inside a bag, you can't see what you're looking for even when it's right in front of your face. Because on Earth, we have kind of a mental model when we're searching for something like our keys. And if they're upside down, we might not recognize them. When you throw things, they travel in a straight line, not a parabola. So if you want to embarrass an astronaut, make them catch after they come back to Earth before they've adapted. And the studies into how our brains adapt are used to help with things like stroke patient recovery. Here I'm learning to use some EVA tools. And you won't see it. This is in the 2G phase where they're doing a pull-up, but we learn how to drill up there, because if you don't brace and push as well, you'll spin when you're using a drill in space, which is makes you look pretty silly to the few thousand people watching you on YouTube. This is how you do CPR in 0G. It's actually much easier than normal CPR because it's all in a single axis. Because if we just did it kneeling on the ground, you'd push yourself off. And so the forces of action and reaction and dynamics are really apparent in 0G, which also makes it an excellent place to demonstrate fundamental physical properties to people studying them and to remind us of them as well. Things like if you do, before I was an astronaut, I went on a plane in the US that also did Mars and lunar gravity. They just fly a different kind of angle of the parabola. And in that, what really surprised me was not that you can jump higher, it was that you come down slower, which of course makes sense mathematically, but it wasn't something that we imagine so much. And that's an important consideration when we're designing things for the lunar surface, particularly liquid and hydraulic systems. But beyond the International Space Station, humans are also going to the moon. And it's pinch me stuff to be qualified for the International Space Station and the lunar missions. And we train for that a little bit differently. There's a lot of overlaps, but out near the moon, you need to be more self-sufficient, right? You need to have a team that works more tightly with less involvement from the ground behind the systems, and usually in a tighter space, because to get things out to the moon takes a lot more effort. You're a lot further away. So if you can kind of imagine in your mind a picture of like the Earth and the moon and their distance apart, usually it conveniently fits on an A4 page, right? But the reality is quite different. This is a scale drawing of the distance between the Earth and the moon. It's 1,000 times further away than the International Space Station is from Earth, 400 kilometers to 400,000 kilometers on average. And that creates a whole different environment. And in fact, there is an acronym that helps us remember all the hazards of the space environment. These hazards apply to electronics and our systems, and they apply to biological systems and the human body. And the acronym is RIDGE, R-I-D-G-E. R is radiation, I is isolation and confinement, D is distance from Earth, G is gravity, altered gravity, so microgravity, 1G, and hypergravity, and E is extreme, enclosed, and hostile environments. And each of those stresses every system and also is an area for research. For example, if we look at I, isolation and confinement, it's not just about being lonely. Our immune systems change. You lose about 1/3 of your immune system in terms of your T cell activity when you're in a confined, isolated environment. Our radiation, when we look out to the moon, much higher radiation being out above the Van Allen belts. In a radiative environment, we cannot fully replicate on Earth. For compute, this means lower abilities to compute. It means greater shielding. It means when we need to have more automation at the edge out there that we have to do it very, very carefully, and with redundant software and hardware. When we look at it on the human body, we don't know really the effects on the female body that well. There were no women in Apollo. So on Artemis 1, before Artemis 2, they didn't put people. They put kind of radiation crash test dummies called phantoms, which are women's bodies with different shielding on them. And they look at the secondary scattering effects in the body. And we got to process some of those one of those dummies in Germany as part of our training. And we're now using that data to have more targeted radiotherapy treatments for women on Earth now that we know better how high radiation scatters in the human body. And the list goes on and on. A really exciting one, of course, is microgravity. That's the one we hear about a lot. So microgravity for research is mind-blowing at many, many different scales. Within cells, there are gravity sensors. They control plants, they control metabolisms of some cells. Some cancer cells replicate faster in space. When you look at kind of the multicellular systems, you can have basically suspension effectively in a solution, right? You don't have anything drop to the bottom or rise to the top because there is no bottom or top. So that means you can have samples that aren't touching each other. So if you put stem cells, they can replicate in space far more quickly than they can on Earth, which is important to produce them for research. You can look at 3D effects. You can have tumors and look at how drugs penetrate tumors to the hypoxic cells in the center. You can look at crystals. Part of the research done at this university and around the world as well is to look at crystals in space. In space, because you don't have fluid mixing due to heat convections and things remain suspended, you basically can grow crystals far larger, far more purely because they grow more slowly and more uniformly across the batch. And that has a number of advantages. When you look at pharmaceuticals, we can see proteins we couldn't see before on Earth. Crystals make up proteins and they make up metals. So we can see potentially hundreds of already identified proteins that we know exist but we can't image properly with Earth-based telescopes. We can also basically reformulate drugs, which can restart the patent timeline. If you're bringing a drug to market on Earth, it takes about 2.6 billion US dollars on average. So to take it to space and you can create hundreds more is remarkable. And this isn't just pie in the sky. There's drugs that have done this. Keytruda is Merck's immunotherapy cancer drug, and they've been able to reformulate this so that it will soon be in a subcutaneous injection for people, reaching more people around the world in more remote settings and through an IV bag in a hospital setting that it is today by changing the underlying structure, which affects its viscosity. Remdesivir, which is a COVID-19 drug that you're given in hospital as an antiviral if you're in a bad way, it can now be given to people with comorbidities like kidney disease in a way that it couldn't before because they could reformulate it in space. And it's the list goes on and on. So it's very, very exciting. But beyond the moon, we're looking to go to Mars, which is absolutely incredible. So the Artemis program is going to the moon to do incredible science in the South Polar region, which is a different area to Apollo, because by understanding the moon, we can understand the early Earth better, particularly the geothermal inputs into climate models, which are one of the lowest fidelity parts of climate models today. We'll also have a presence on the moon in the same way that we have a presence in Antarctica, which is important for international relations and for how we work together. And we'll also be the innovation room for the broader space sector that we rely on today more than most realize. But as we go to Mars, there's a lot to be solved. And so to be out in solving it, we'll be able to address, I think, a lot of different challenges on Earth as well. One example is we don't have the systems to create 3 years worth of food supplies that meet astronauts' nutritional needs, let alone be able to refuel a rocket without any people there and take off from Mars and return. So there's things to solve, but they're not impossible. So it's often thought the first person on Mars is probably in a classroom in a school or university in the world today. And who's to say it can't be an Australian or a New Zealand classroom if we want it to be. So yeah, I think it's an exciting future ahead of us, and Australia and New Zealand, the world wants to work with us in space, and we're massively punching above our weight on the world stage. And so to that, I say, let's up our weight class. We can do a lot more than we imagine we can. When I was overseas working, I'd see Kiwis and Aussies everywhere contributing to the space capability of other nations. And the same conversation would always come up between us, which is, wouldn't it be great if one day we could do this at home? Now, increasingly we can, but we're on the cusp of perhaps being able to do even more, which is very exciting. So I'm happy to take any of your questions as well.
Thanks, Catherine. Got a couple of mics that are going to be coming round, and my question is there an age limit to becoming an astronaut?
Well, it changes. So in the selection I went through, the upper age limit was 50 to apply. So, but the time before that, which was 12 or so years before, it was 37 or 38. So I would have just scraped in. I'm 41 now. But yeah, basically, as long as you're performing, the Europeans were looking to be able to get a couple of space missions out of their astronauts, which you can do between 50 and 65, right? Which is their retirement age. But we do still have astronauts flying as commanders of missions in their 60s. The US astronaut with the most experience in space is Peggy Whitson, who now works for Axiom Space. But she's in her mid-60s and still commanding missions and kicking goals. So it's also Don Petit, who's similarly flying for NASA.
I was prepared to be disappointed then, but I've still got a few months. So.
So for me, at the undergrad level, I did a double degree. So that was in Bachelor of Advanced Science, majoring in physics with maths, geology, and chemistry subjects there too. I have a Bachelor of Engineering with honours. I think you have the same structure, like a 4-year degree. Yeah, and that is in aeronautical space engineering, because it's before there was accreditation in Australia to have the full space piece, but it was a combination of aero and space. From a master's degree perspective, I did a 2-year double master's overseas. One was in space technology, a Master of Science, Space Science and Technology, and the other was Master of Science in Astronautics and Space Engineering. So I've always been kind of educated with one foot in science and one foot in engineering, and that worked really well for me because the science was the why to engineering's how. And I actually found engineering really dry for the first couple of years. It was a bit of a slog, to be honest, but it was when I finally got to being able to be creative with it, like properly creative and not just building things people had built before or solving problems that were already solved, that I really fell in love with it. And I've been able to be an engineer for my whole career, but always working with scientists to help develop what they want to know. And you have a process in something that we call mission systems in the UK or mission architecture in the US, or early projects. So going from the first kernel of an idea to a feasible first design, usually at like PDR level, when you got your requirements set, validated, and the first design nutted out. That was my specialty. I started in thermal engineering, then I did early phase engineering, and then full systems and back to early phase. And that's kind of creating order out of chaos. And to do that, you need to be able to iteratively move around with the scientists to adjust what they want to know to what's feasible and what works programmatically and technically as well. Yeah, so the undergrad was in Australia. They were both in Australia, University of Sydney. Postgrad, I did a program called Space Master, which is a cute name for a group of universities under an European Commission program called Erasmus Mundus, which does a lot of master's programs for international and local students, where it's 2 years, 2 degrees, which is a nice deal. And the second year, you pick which university you want to go to and specialize, and the first year is common. The thing is now, though, that at that time, to specialize in space, I felt it was important to go overseas. You don't need to do that in Australia, and I'm sure New Zealand too. There's really good degrees here, postgraduate as well. Of course, if you want to live internationally, it's an opportunity. Just bring the knowledge back home, right? Because there's a real delight in being able to do that as well. So the universities I went to fully answer your question, in that double master's degree, the first semester was University of Würzburg in Germany. Second semester was Luleå Tekniska Universitet, which is a university in Sweden, and the far north in Kiruna above the polar circle, which is really cool. And then I did a summer at NASA Ames, and then I did the third semester in the UK from Cranfield University, which is where I got the second degree, and then the final semester at the European Space Agency doing my thesis in the thermal team. It's a great field if you like to travel, because you're always working with an international team and you can find common ground in the excitement you have for what you do, which is great.
I've just got two real quick ones. A, do you have a pilot's license? How
So I had a license when I was a teenager. I did aerobatic flying, but when I didn't join the Air Force, so I tried out to be a pilot before I went to university. I got through, I got my acceptance letter, and then was quickly medically postponed because I had a low reading in one of my blood counts and they wanted to investigate it. And that's why I went and did science and engineering as a degree while I was waiting for that to be tested. But, you know, then I started getting scholarships to NASA and stuff, and I was hooked. So I didn't go to be a pilot when they cleared me as just being low on the bell curve. So at that point, I couldn't afford to pay for it myself. My parents were helping me out because I thought it would be my career. So it fell away. But flying is an excellent skill to have. If you want to be an engineer or scientist of any kind, you're living it operationally, and it's an excellent basis to be an astronaut. It's one of the desired criteria to have a pilot's license. I picked it up again recently. Normally you learn it again on astronaut training, but I was only covered to do the qualification training. My classmates have learned to fly since, those that weren't already pilots.
And then the second one was growing up in Australia, I can imagine to be obviously quite similar to New Zealand. That there is available space science education, or was it at the time is still now largely one of those dream subjects that kind of has gone?
Yeah, so at high school, I mean, it wasn't really there at all. And at university, Sydney University, where I went, was the only university in the country which had the word space in the title. In fact, I picked up the engineering part of the degree because of that. I didn't really know what engineering was. I wasn't particularly hands-on as a teenager beyond liking to fly and tinker a bit with the planes. But yeah, now it's changed. There are good capabilities, and you don't have to go overseas. You can, but you don't need to anymore. And one of the great things at the moment about having the Australian of the Year platform in Australia means that you become quite mainstream in what you talk about. And I've been able to inform people a little bit about the opportunities in space. Basically, there's a lot of opportunities in space career-wise. It's still a small industry, but the applications are so broad that you can put the word space pretty much in front of almost any field and make a job out of it, if that's something that excites you. It can still be seen as out there, but there's more and more success stories. Like in New Zealand, Rocket Lab has huge credibility internationally and at home for those that can crack in, and a lot of spin-off companies and related companies as well. But yeah, we don't have the full ecosystems that you see in, say, a major space power.
Any, yes, Sandra, so just
right here. The first is, since smaller people tend to need fewer calories, do you think the first mission to Mars will be an all-female crew?
I don't know. I mean, the feedback we're getting is you know, mixed teams are performing quite well. From a calorie perspective, it depends if that's a limiting factor or not. I think it's going to be being able to fulfill the full nutritional profile that matters a lot. Right now, you get all sizes of astronauts. Like I'm the shortest in my class, the equal shortest, and I'm not a short person. To the point where we still have to like pad out our spacesuits. The next generation spacesuits will hopefully be a little bit more diverse. We are seeing more women becoming astronauts finally, because astronauts are recruited out of technical fields which are historically very male dominated. You know, it took a long time to be able to have a lot of women. To date, only just over 10% of professional astronauts have been women. There's been 84 women in orbit, also including non-professional astronauts. Some have gone up commercially. And the first woman to go to space went up 63 years ago, Valentina Tereshkova from the Soviet Union. It was 19 years later that we had the second woman who was an astronaut, and she was handed an apron as she entered the space station, and not as a joke. And then after that, it was Sally Ride, right? From the US. It was the first US astronaut. And I think all the women that have done this incredible work have absolutely demonstrated that it's not a capability question and that women belong, wherever the future is being written, holding the pen and the throttle, right? So it's important, not just because everyone should have the chance to be able to strive, but because diverse teams are often more performant teams. There's lots of kinds of diversity, but gender is one of them. But also that medical test subject piece is so critical and important as well. More and more we are seeing women's health be understudied on Earth. It is very understudied in space. When I went through the astronaut selection, thinking I might not get through or trying to get hints about what to prepare for the medical round, I went and looked up papers from the previous round. And at that round previously, there were 55 people left. They left the women off all the research papers because at 5 out of 55, they weren't statistically significant enough. So that was quite remarkable. That being said, my class is 50-50. That wasn't a quota, although there was an effort to advertise the selection to women. We were told it had no bearing on the selection. And last year, NASA had their most recent astronaut recruitment, and they're all ASCANs now going through training. And for the first time ever, that class had more women than men. And almost all of them had military experience. So it wasn't that they changed the criteria at all. So that was exciting to see. So we'll see what the future holds there.
Thank you.
First crew to Mars, who knows?
Thank you. And then my second question was, I remember in the beginning that one of your qualifications was in debris removal.
Mhm.
I was wondering what you felt the future of space pollution was like, especially in the Southern Hemisphere, and how concerned you were about things like Kessler syndrome.
Yeah, so for those that might not be aware, Kessler syndrome, the Kessler effect was something that was kind of published about decades and decades ago. I think it was maybe the 60s. I can't remember the exact date. Basically, it's based on mathematical equations that are quite simple, just exponential equations, saying that when we'll get to a point where even if we launch nothing more to space, the cascade effect of collisions will mean that we just get an entire debris cloud and everything becomes debris. And the consequences of that are quite dire because you can't then put satellites into space to provide all the services we rely on, like the timing data that underpins our banking, our energy, and our transport systems, for example. So it's thought by most that we've passed that point. So it's not enough just to remove what we're putting up there, but we need to also remove the dead ones that are up there. The problem is that's a tragedy of the commons challenge because to remove a satellite costs a satellite, right? There's a lot of effort around the world from space agencies, particularly looking at this issue, and a lot of discussion and a lot of good intent from most space actors to do the right thing there. The advent of mega constellations in space is going to challenge it. One way people are thinking to manage it is to have like special orbital shells. Because if satellites collide, typically debris spreads out like in orbits and eventually shells, which are just for those constellations to protect them and also to protect others from them. There's different concept of operations you can use as you put up a constellation. For example, with Starlink, the satellites are launched into quite a low orbit. So if they don't turn on or work properly, they'll be deorbited or they'll degrade in their orbit well before they get to a higher point where they're hard to remove or cause more debris. But in terms of having concerns about debris in the Southern Hemisphere, debris affects all hemispheres. In Australia, we've had a lot of space junk hit Australia in a real public way over the past few years. And at the Space Agency, we have a space monitoring team that can say immediately what that is and tells people not to approach it and so on. But it's certainly something that needs to be and is being addressed. I can hear you fine. I can repeat the question if I need.
I just wanted to ask about the research and the experiments that you developed in space. Are you able to develop your own research or do you have to join a team? How that happens?
As an astronaut or as a scientist? Or?
As a scientist, yeah. Are you able to develop your own research?
Yeah, so there's different ways to do it. So if you're from a country with a human spaceflight program with access through that, typically what we're seeing is countries, say like France, Germany, US, Canada, Japan, UK, when their astronauts have missions or their space agencies have missions, there's a call for ideas and they put in their project and it's funded through the national science budget. We're seeing increasingly more opportunities for countries that do not have astronauts to access space commercially, for example, by paying companies to access the space station on their behalf, but typically that limits you to small experiments with a limited amount of astronaut time. So the best way, if you want to be a scientist that puts things in space, is to either join and collaborate with research partners from those countries because they kind of get cheaper access to space, or to access it commercially yourself, and longer term to look to your government to stand up that kind of capability. One thing that's quite exciting in Australia's case is the Australian government is now engaged looking at an astronaut mission for Australia to fly me to the space station in the next few years, which would be really exciting because typically you fly with a suite of payloads. My classmate Sophie, who's up there right now, she's got over 200 experiments, right, to take part in and support. You also go up with an education program and a supply chain access program for your space sector as well, but the research comes from every sector. It should be really, really broad. So yeah, there's a few different ways in. And it's becoming easy to access, but with the International Space Station coming to the end of its life around 2030 or so, that's going to disrupt things for a little while. Right now, it's really mostly government research up there or government-supported commercial research. In low Earth orbit, after the International Space Station, what's the intent is to have what's called commercial LEO destinations, but that's going to be one or more really small space stations, relatively, maybe one module, like the size of a caravan or bus, right? And the idea is that companies will run those. It'll still probably mostly be government research and pharmaceutical research commercially, but you do have industrial customers too, but that's more likely to be paid by cash. And what most countries do now is they build something, contribute to the infrastructure, and that offsets the costs. Like Canada makes big robotic arms, Japan's making a self-driving EV for the moon with Toyota for their astronauts to go to the moon. And yeah, of course, there's the Artemis program as well. New Zealand is an Artemis nation. Australia is an Artemis nation. There's over 50 now, and that will help New Zealand to get involved. A lot of the work for Artemis from a research perspective is done through space agencies. So you should go to the New Zealand Space Agency to say, this is what I need and what I want from a research perspective. There may be opportunities to also pay directly to some of the commercial robotic landers that offer services, but for quite some time.
Just coming up on 3 o'clock, so up to very, very short. Should be a short question. One last.
I'll do a short answer.
Hopefully it's short. How would you recommend getting involved in the space agency or just anything to do with space as a university student?
As a university student, you are in the wonderful position that you can get internships. It's a lower barrier to get an internship than it is to get a job, but it's a stepping stone to a job. So for internships, do as many as you can handle, as you can afford, as you can make time for, because that is what sets you apart. I'd say for your first 3 years out of university, it's really hard to tell if you're better or not better than the person you graduated with, no matter what your marks are. When I look to recruit people that are quite young, I look for things that set them apart. Internships, what they did for their thesis. Yeah, I look at marks a bit, but I don't really know how to judge marks between universities, particularly internationally. So internships also not only teach you about what you like and what you don't like, but they build your network and they help you to see what's out there. So for me, one of the internships I did was my master thesis at the European Space Agency in the thermal team. I was working on space lidars, Earth Care and Aeolus instruments. And I thought I loved analysis. University is really analysis focused, right? But after 3 months, I was like, dear God, I want to work in a team. And I saw further down the corridor from me, there was the advanced concept team, which like basically developed on rapid fire missions like a sport and competed between each other. And I was like, that's what I want to do. But I didn't know it even existed. So in New Zealand, I would apply to every company, particularly apply to companies that have new money or new projects because they will be needing support. And if you can, apply internationally too. It's easy to travel overseas when you're young. In Germany, they're a really good place to do an internship because they speak English pretty well. they have a lot of internships in their engineering program, so they're set up for it. You can cold call them basically and just cold apply. So cold apply everywhere as an intern, and that's how I would do it.
Thank you.
Right. But I'm sure we could spend a lot longer talking, and maybe you're happy to spend another 10 minutes afterwards. But we should draw things to a close. And it's been fascinating. Thank you so much.
Thank
I'm
you.
so honoured to have you here and come and talk to us about your career and life in soon to be in space, but what a greater space. Yeah, join me please in thanking Katherine for flying in.
Thanks everyone for having me. Good luck in what you choose to do.
Yeah, and see you again in a few months.